Okay, so it's a great pleasure to receive today Professor Maria Bras.
What does the divergence gives us?
This is a very
Achievement कहाँ से कहाँ होता है कि
area of Semigroups, Numerical Semigroups. She has already so it's a great honor for us to receive her and for the second time. So thank you very much, Maria, for coming to our small university. It's a great honor to receive you here. And so, well.
Okay, thank you very much. And thanks for the invitation. It's always a pleasure for me coming to Brazil. I feel like every time I come, it's better and better. The first time we met with Cicero, it's more than 15 years ago. And I didn't think at that time that I would come here so many times. So, thanks for the invitation. And one very important thing is that I came here in 2020, I think. And in the audience, there was a woman, and now this woman is working with me. She came for a PhD in Tarragona, and this has been a very nice experience also. And at some point, I will explain some of the work I'm doing with her, although this is not the work, this is not the topic of this talk. Okay, so today I'm going to talk about numerical semigroups and the applications of numerical semigroups to algebraic geometric codes. Okay. I will start with some basic notions on numerical semigroups and some notions that we need in the area of coding theory related to numerical semigroups. And then I'm going through some topics in coding theory in which we have applied these notions of numerical semigroups. Okay, some of these topics also have to do with the research that Cicero did before, and Alonso, Guilherme, Luciano in the audience, Eric, Rojas, and I'm sure I forget many of the people that work on this, but there's an important community in Brazil also working on these things. First of all, a numerical semigroup is a subset of the non-negative integers that contain 0, is closed under addition. Every time I add two things in the semigroup, I need to obtain something else in the semigroup. And the number of things that are not in the semigroup but are non-negative integers, this is finite. We call these elements the gaps, and the number of the gaps is the genius. As an example, if we take 0, 4, 5, 8, 9, 10, and everything that is at least 12, then here I have 0. If I add any two things here, 8 plus 5, for instance, 8, 10, 13, which is inside, every sum I can do with 2 elements here, it is another element here. And the complement is finite because from 12 on I have everything, so the complement is contained here, which is finite. The gaps are the elements that are not in the semigroup, and the non-gaps are the elements of the set. Because of the third condition, there is always one element like here, the 12, for which we have everything beyond, and this is this number is called the conductor, we'll see later, and the gap before it, it's called the Frobenius number. It's the largest gap, and the conductor is the Frobenius plus 1, is the largest gap plus 1. And there are some examples. This is my favorite example. It comes from music theory. When we play acoustic instruments, there's something called the harmonics, And when we play one note, there are many other notes that sound at the same time at a higher pitch, although it's a lower intensity, so it's not that obvious to hear them. But they are all there, and those are the notes. First, we have the octave of the fundamental note, the octave, the fifth over the octave, second octave, and so on. And if we match all these harmonics in a tempered system with equally separated semitones, what we obtain is a numerical semigroup. In this case, it's when we match it with 12 semitones, which is what we use in Western classical music. And so if I separate each octave by 12 semitones, then I can count the distance between the fundamental to each of the overtones. The distance of the fundamental peaks at 0. The distance to the first octave is 12 because it's the number of semitones in an octave. Then the fifth is at 7 semitones from the octave, so it's at 19 semitones from the fundamental, and so on. If I press this key in a keyboard and I look at the strings below, these strings will start vibrating, and they coincide exactly with the keys that are at these distances from the fundamental, 0, 12, so on. And this is indeed a numerical semigroup. And the reason for which this is a numerical semigroup is because the overtones of an overtone must be overtones of the fundamental note. And this gives the condition of being close convergence. I especially like this semigroup also because at some point we proved that it's unique according to 3 conditions. It's the unique semigroup that satisfies 3 conditions at the same time with maximum separation of the first interval. And the 3 conditions are, one is drawn here. This is a fractal semigroup in the sense that I consider the distance of the first interval. Then at the same distance I have one partition at a given portion. Then the next jam of the first jam, if I add the first jam to here, I obtain the same partition I had before, and every new interval is divided in the same portions. This is a fractal division of intervals. This semigroup satisfies this. Another thing that this semigroup satisfies is that has a lowering behavior in the sense that, for instance, if I consider 19, which is lambda 1, lambda 2, lambda 3. 19 corresponds to 3. 24 corresponds to 4. If I multiply 3 and 4, the indices, this is 12. I go to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is exactly the sum of lambda 3 and lambda 4. And this happens for any pair I take here. If I multiply the subindices, I go to the term with this index, and this term is the sum of the first 2 numbers. This is logarithmic behavior. So we have fractal behavior, logarithmic behavior, and one third condition is that if I take the first, the third, the fifth, and so on, this is again a numerical semigroup. And all these properties that I explained here, they all have a translation in music theory, because there are some instruments like a clarinet that don't have all harmonics, but exactly the ones that are flat position. So this is, I would say, the most special numerical semigroup that I've ever met. And on the other hand, we have these Weierstrass class semigroups, which are probably the most important from the point of view of applications. We suppose we have a projective, non-singular, geometrically reducible curve. We distinguish a rational point in the curve. And we consider the ring of the functions that only have poles at this point P. We call this A. And for all these functions in A, except for the 0, we consider the pole order of these functions at the point P. We put a minus at the beginning in order to get positive values. And it's easy to prove that 0 will be in the semigroup because it's the order of the constant function 1. The sum of the orders of the functions is the order of the product of the functions, so the sum is there. And also the number of things that are not in the semigroup is finite. And this, because of these three reasons, these binary stress semigroups are numerical semigroups. One example that I will use later, it's the Hermitian curve. It's given by this equation here, and it has one unique point at infinity. If we look at the pole orders of the functions that only have poles at infinity, these functions, they have order 0, 4, 5, 8, 9, 10, and everything from 12 on. This is the first semigroup I wrote as an example. Okay. So, another important thing of numerical semigroups is that since they are included in the non-negative integers, we can enumerate the terms. So we can say first, second, third, and so on. This gives us what we call the enumeration. We call lambda 0 the first element, which is 0, lambda 1 the first non-zero element, and so on. Okay. Now, once we have a numerical semigroup, we can define a sequence nu I. Nu I counts for each I the number of non-gaps that can be subtracted to lambda I and still obtain an element in the semigroup. Let's see. For instance, in the Hermitian curve, here we have the semigroup 0, 4, 5, 8, 9, 10, 12, 13, 14, and so on. Lambda at nu 0 will be 0 because there is only one element which I can subtract to 1. That's the only element I can subtract to 0 is this. If I look at 10, for instance, the elements of the semigroup that I can subtract to 10 are 10, 5, and 0. This is why in this case, the corresponding nu is 3, because I can subtract 3 things. For 12, I can subtract 0, 4, 8, 12. This is why in this case nu is 4, because I have 4 elements. This is an important sequence related to numerical semigroup, and now there's another sequence which is the Tau sequence. In this case, for each element in the semigroup, we look at all possible sums of two smaller elements in the semigroup, and of all these sums, we take the one in which the elements are more close, and we take the index of the smallest one of these pairs. For instance, here, if we look again at 12, 12 is 0 plus 12, but it's also 4 plus 8. I draw in blue the two elements that sum to the semigroup element, such that they are as close as possible. And in this case, Tau counts the index of the smallest one of this pair. In this, for instance, here, 4 is lambda 1, then Tau is 1. Here, 8 is lambda 3, then Tau will be 3. And so there are three tricky definitions of the bit. It's really very simple. Okay, then those sequences which may seem kind of capricious they are equations, as everything in mathematics, but they arise from problems in coding here. But if we go back to the theory of numerical semigroup, we find interesting results related to these sequences. For instance, there are results saying that if we know the new values of a semigroup, this completely determines the numerical semigroup. So two different semigroups will have different new sequences. And the same happens for tau. If we are given the tau sequence of numerical semigroup, then we can determine the semigroup from this tau value. And finally, both sequences have the property that you need the whole sequence in order to obtain the semigroup, because every finite part of the sequence is shared by infinitely many numerical semigroups. So it's something that determines the semigroup, but as far as you have the infinite sequence. Okay. So now we can see how all these things will have relationships with coding theory. A linear code, probably you all know, but just let me repeat what you already know. A linear code, which we call C, is a vector subspace of Fq to the n, where Fq is the finite field of Q elements, and n will be like the length of the words in the code. That n is the length of the vectors in this vector space. We call the vectors in this space words. So the n will be the length of these words. And the dimension of the code will be the dimension of C as a linear subspace of Fq. We can consider the orthogonal space of a code, and this is what we call the dual code. Those are all the vectors in Fq to the n that multiplied by the words of the code are 0. And this dual code plays a very important role in order to determine also the code. And given this dual code, a parity check matrix of C is a matrix that has as rows a base of the dual code. So we can determine a code as the set of solutions of a linear system whose matrix is this parity check matrix. So we will consider codes C, for which we will have a parity check matrix. And the code will be the set of words that multiplied by this parity check matrix are 0. Okay. Now we go back to the same scenario as before. We have a projective curve with singularities. We have a rational point. The ring of functions having only poles in this point. The bidirectional semigroup that we already presented at this point. The enumeration of lambda. The enumeration, this means that we can say lambda 0 for 0, lambda 1 for first non-zero element, and so on. Then we also enumerate some functions, f0, f1, f2, and so on, such that fi has order lambda I. Has pole, in fact, has pole order minus lambda I in the. Then we distinguish n rational points, all of them different, and also different from the rational point B. And we consider the evaluation map, which takes all the functions in the ring to the evaluation of the functions to each of the points P1 up to Pn. This is well defined because our functions f belong to A, and so they don't have poles in P1 or Pn. So everything is well defined. Now we'll define C sub I as the linear space which is orthogonal to the vectors that we obtain in this way when we evaluate functions in A with bounded pole order, bounded by lambda I. This is the same as evaluating all functions in the Riemann-Roch space of lambda I and taking the orthogonal of this space. If instead of an index I, we have here a subset of indices, we can consider the space generated by the evaluation of all functions whose index belongs to the set. Now we don't have all functions with order up to a certain bound, but we have all functions with disorder and disorder and disorder with the orders given by a finite set R. Is it clear the difference? The difference between these two notions will be fundamental. For the top, we distinguish what we call standard codes, in which disparity checks are given by evaluating all functions up to a given order. And here, the non-standard codes will be when we evaluate certain functions, but not with all the orders up to a given one. Okay. For instance, we take F16 defined by these congruences, these congruence classes. We call alpha a class of X, and the Hermitian curve, as defined before with this equation, has 64 more points apart from one point at infinity. We can, enumerate all points. And in this case, the basis functions are f0 will be the constant one, f1 will be x, f2 y, f2 is x squared, and so on. So, for defining these codes, what we do is evaluating these functions in all these points. We will construct a matrix in which every row is the evaluation of some of these functions in the points. For instance, here, in the first row, everything is 1 because this is evaluating the function 1 in all points. In the second row, we have the x coordinates of all points 0, 0, 0, 0, 1, 1, 1, 1, alpha 3, alpha 3. This is what we have here. And so on. At each row, we evaluate some of these functions at all the points. For the standard codes I was saying, we will use as parity check matrices which will be this matrix up to a certain point. In the case of non-standard codes, we will just select some of the rows, not all of them. This is an example. In this case, this will be C3. We evaluate all functions f0, f1 up to f3. But if instead of taking a subindex, we take a subset of indices, we just consider the rows corresponding to these orders. Okay. Now, now we are going to analyze these codes, but we will use these R sets to optimize the dimensions of our codes. We will say, I want to correct all errors of a certain type, then I don't need to have all rows up to a certain point, but with just some of them, it will be enough, so I will get better codes. Okay, so I say that there are T points which are generically distributed if there's no element in A of with pole order less than lambda t that vanishes in all of them. For instance, 2 points are generically distributed as far as they do not belong to a horizontal line. So there will be pairs of non-generically distributed points, but most of them will not be in a horizontal line. If we have 3 points, they will be generically distributed if they do not belong to the same line. So we see that being non-generically distributed is something very unusual. And the same for 4 points. Well, okay, there's a point missing here. If I have 4 points, they are generically distributed except if they belong to an equation of order 2. So, okay. Now, we will identify the possible errors in a word. Our words are defined as I said before, and we will consider errors. Errors will be words which are almost zero everywhere except in certain points, and we will consider generic errors, those errors which are generically distributed. So most of the errors will be generically distributed. If I have a word with 2 errors, the 2 errors, I can assume that in general they will not be in a horizontal line. Or if I have 3 errors, I will assume that they will not be collinear. In general, there will be exceptions, but the exceptions are a very small portion. So this is the idea in this selection of specific rows, that restricting the errors to be corrected to these generic errors, then we will get quicker decoding requirements. We will be able to take away some of the rows in the PPGMAT, and so we will obtain better dimensions. And still, we will be able to correct most of the errors because we consider that most of the errors will be generically distributed. Now, Feng and Rao proved the result in 1995, a celebrated result. They stated in another form, but using the notation that I just explained, the result would say that C sub R can correct all error vectors of weight T if this R contains all indices I such that nu I is more than 2t plus 1. This nu I is the sequence that we saw before. And this is a result of my PhD thesis. Here we concentrated in these generically distributed errors, and we saw that CR can correct all generic errors of weight T if R contains all i's with tau I smaller than T. So the new sequence would be related to trying to correct everything, and the tau sequence would be related to trying to correct just generic errors. So for correcting T errors of any kind, we will consider tilde R as the indices that satisfy the requirements for decoding. And R of T will be the standard version. This would mean taking these rows and all the rows in between so that we have all rows up to a certain point. This is what was used at the beginning, because at the beginning they always considered codes of the type C sub I, standard codes. But at some point, Feng and Rao brought this improvement of just taking away the rows that are not required for the code. If we want to correct 2 errors of any kind, we need to determine what are the i's such that nu I is more than 2 times 2 plus 1, which is 5. So we need to take all functions such that this nu is 1, 2, 3, or 4. 5 and 6 will be discarded. So those are the rows that I need, I can discard those two. If I want still a standard code, then I will need all rows up to this one. If instead of trying to correct anything, I just restrict my ambitions to correct generically distributed errors, then I will just take the rows for which tau I is more than the number of generic errors I want to correct. And this is the version if I want to use standard codes. In this case, I look at the tau, and I consider those places in which tau is smaller than 2. And this corresponds to the first 5 rows plus this row here. So I will need these rows for correcting. If I still want standard codes, then I need to add this row. The code that I will obtain here is a code that will not correct everything, but in general will correct everything because it will correct all generically distributed. Okay, and this is a drawing of the behavior of these codes. If I want to correct everything and using all rows up to a certain point, which was the classical case, then the number of parity checks I need is this set of blue points, as the number of errors increases from 0 to 10. If I want to correct all errors, but only using the rows I really need, I will use this number of rows, the ones in yellow. If I try to correct only generic errors, but using standard codes, I will need these numbers of parity checks given by the green points. At some point, yellow is better, and at some point, green is better, but the very best option is trying to correct all generically errors and only with the rows that I will need. And this is what is obtained by using the number of rows given by the red points. Okay, so if I want to compare all these constructions, I will need to start the increasingness of nu, the increasingness of tau, because this will give me the difference between taking standard codes or non-standard codes. And if I compare nu and tau, this will allow me to compare the option of correcting generic errors from the option of correcting everything. Okay, and so this is one kind of results where numerical semigroups were used in coding theory. But there are many other results in which semigroups are used. And for instance, Gale and Matsumoto, they bounded the length of algebraic geometry codes using bias class semigroups. These algebraic geometry codes that we described, the length of them is given by the number of points which are different than the point at infinity. If we want codes of maximum length, we need to take all points except the point at infinity, and so we need curves with many, many points. And the length of these codes will be bounded by the number of points, and we have bounds for the number of points of curves. This is one celebrated bound. So this is related to the genus. The number of points of a curve of genus G over SQ is at most this amount here. But here we are only using the genus of the curve. We can go further and specify the bias class semigroup of the point at infinity or some other point. And then we Gale and Matsumoto bounded the number of points that a curve can have with this bias class semigroup. And this is characterized by the generators of the semigroup and counting the number of elements that we have in the semigroup, and we take away all things which are multiples of the elements of the semigroup plus the semigroup and so on. This is a formula, the formula we have here. And using this formula, you can obtain several results if we consider special kinds of semigroups and so on. Okay, another place where we use numerical semigroups is in the analysis of sequences of codes. Here we work with Alonso and Luciani. But one notion that we need here is the notion of ideals of numerical semigroups. First of all, we have one result on numerical semigroups that says that the Frobenius number of a semigroup of genus G is at most twice the genus minus 1. This is something that translates to having a generalization of this for the conductor, the corner of a semigroup when the semigroup is not just in the non-negative integers, but the non-negative integers to some power. Okay, this is a result. This is a Frobenius number, and it follows from the Richard's principle. Now, an ideal of a numerical semigroup is a subset of the semigroup, such that if I add the semigroup to the ideal, all the things I obtain are inside the ideal. And one goal is finding a bound for the Frobenius number of the ideal, not just the Frobenius number of the semigroup, but the Frobenius number of an ideal. And we found a bound which is a generalization of this, because this would be the case when the ideal is the whole semigroup. Okay. If we call the number of elements in the semigroup which are not in the ideal, then the Frobenius number of the ideal is at most this difference plus 2G minus 1. In the case when the ideal is the semigroup itself, this is it. And so we obtain the bound that we obtain. This bound is sharp. We have ideals for which this is an equality. And the ideals for which this is an equality are called maximum sparse ideals. This bound has been applied to bound generalized spanning weights of AG codes. This is some parameters that are used in coding theory. I will not give here the details, but this ideal is something that has had an application to study generalized spanning weights. And now we are going to see another application. We say that two codes, the other application will be related to the sequences of codes that we have been working with Alonso and Luciani. Two codes are said to be X isometric if there is a constant X, such that one code is the product of X times C, where the product is the component Y product. Now, we are interested in sequences of codes which are subsequently contained, each code contains the next one. Each code has a dual. The dual of this code will be this code here, the dual of this code will be here. If a code is contained in another code, the dual of the second code will be contained in the dual of the first code. This is why here the sequence of the duals is in the reverse order. And why we are interested in the case in which we have this sequence and its dual, which satisfies this property. There is one unique X, one constant vector X, such that this code is X isometric to this one is X isometric to this one, and so on, always with the same isometric vector. In fact, we have been going further. We found cases in which these are exactly the same, because the X, we have found several examples in which this X is constant 1, so the two sequences are the same. Okay, Now, sequence of codes is set to satisfy the isometry dual condition if there exists this constant vector such that Ci is X isometric to the dual of dual codes of C sub n minus I, which is what I explained here. Okay. In the case of algebraic geometry codes, if we have P1 up to Pn different rational points of curve and P the point of infinity, the Weierstrass semigroup of P is this here, this thing here. We consider if W is the Weierstrass semigroup, we consider W star as the values in W such that the code Ci has a jump with respect to the previous code. Because it could be that Ci equals Ci minus 1. But if there's a jump, especially a jump on the dimension, then we add this index to W star. It can be proved that there are n values in W star. And we can go to some results related to this and produce it then in terms of ideals. And so one result of Gael, Numerical, and Torres, if we talk in terms of ideals, it can be read as this. Always W minus W star is an ideal of W. They prove this. Not using this terminology, but they use the related result. And also that this sequence of codes satisfies the isometry dual condition if and only if this ideal is what we said maximum sparse, in the sense that its Frobenius number is as large as possible. And this is what I wanted to explain. But now, if I have 1 more minute, I would just like to mention some of the work that we have been doing with Mariana Rosas. I met her here in a conference like this, but 4 years ago. So it's a pleasure for me. I will just mention it. Okay. Mariana's online? Okay. So happy to have her here. I will just mention the idea behind her work, but okay. So one problem in which I've been working for a very long time is the problem of counting semigroups by genus and to see how many semigroups I have of genus 0, genus 1, genus 2, and so on. And the way to analyze this is putting all semigroups in a tree. Here, there's only one semigroup of genus 0, which would be here in the group. There's one semigroup of genus 1, which would be here. From this semigroup of genus 1, taking away elements, we can obtain 2 different semigroups of genus 2. And from each semigroup, we can obtain semigroups of genus increased by 1 by taking away elements. And at the end, we get this tree. One still open conjecture is proving that at each step, we have more nodes at each level than in the previous level. This is still open. And one curious thing is that we realized that there are some finite chains in the tree. Here the infinite chains are painted in red, but most of the numerical semigroups belong to chains which finish at some point. There are some semigroups which don't have descendants, and all the previous semigroups, if they don't belong to infinite chains, then they have finite number of descendants. And it's curious because this is a tree which grows exponentially, but one can observe that it's made of finite parts. And this is something that we had observed, but we couldn't prove. And with Mariana, she proved that there are more semigroups in finite chains than in infinite chains. And very recently, we proved that we proved that indeed the number of semigroups in infinite chains, the portion of these semigroups with respect to the whole set of numerical semigroups, if we fix the genus, this approaches zero, as the genus approaches to infinity. And that's it. I'm happy to finish with the result.
Okay, so thank you, Maria, very much for this very nice talk. Thank you for taking one of our students as your PhD student. So, any questions or comments? So I know that you have some conjectures about your first conjecture about the growth of the number of semigroups with certain genes. That a certain rate would approach the whole number. But I recall that there was another conjecture about the sum of the number of some semigroups that would, in a way, characterize this. Like I think it was something like mg minus 1 plus mg would be less or equal.
Yeah, we always have this.
So, but this is already proved or not?
No. What is proved, it's this. This which this would prove this is asymptotical, but it's not proof that at each step this happens.
Yeah. So this is a very nice projection from Maria.
This would be the big version. This is still open.
Wow. So, well, this is something for you to think. It's not difficult to understand the trajectory, it's very difficult to prove maybe, but it's something for you to think on your vacation. Okay, so thank you, Maria, very much. So we thank the speaker again. Então pode encerrar a reunião aí.